Hello everyone and welcome to this second video when we go into a little bit more detail around acidity and erosion as part of this project funded by the North East Catchment Management Authority and in cooperation with Chestnuts Australia, Connexus Global and Trevor Ranford Consulting. In the first video we touched on soil health as a main driver or a main aspect of management of soils throughout the Northeast. And more broadly, I guess. In this presentation, we've split it into two components. One about acidity and a little more detail than we covered off in the first one, and a brief discussion on erosion as the second part of that as well. We're not going into any great detail around management. We still look forward to getting together face to face with everybody and being more or providing more specific program around management. If we've still got those challenges through the year, we'll find another way of doing another video or filling in the report requirements and covering that off so everybody's got access to this information. Again, we're working through this as a broader soil health framework for managing soils, and again, not going into that in any great detail, but certainly just taking out the two aspects of acidity and erosion and just learning some basics around how both of those things work, and then later on looking at how we might manage them more specifically. We have taken a number of analysis from two sites, one red clay soils up in Stanley in the northeast on a chestnut property, and another in Myrtleford on a riverbank, river flats, loam type soils that we can be a bit more specific about, showing people what to look for on different soil analysis that can help them look at some numbers that can contribute to assessing improvement or decline over time in their soils. Again, thank you to Native Seeds for providing Microlina for a demonstration plot, and also cooperation for TAFCO RapidFert and for soil analysis and lime requirements as we work through this project. There's been, and this is only one, but there's been a very, very large number of inquiries and significant research throughout Australia over a long period of time in respect of managing soil acidity. It is a natural event in an agricultural system, certainly in the northeast of Victoria with high rainfall, and we'll touch on a little more specific how that works in just a moment in causing acidity. But this is a major issue in Australia. It is significantly more degrading in our soils than salinity, which is something that gets commonly brought up in the news. Acidity is a little bit harder to understand. Certainly some different challenges in different soil types in its management, but a far greater impact. We're also seeing now, when a report like this from 16 or 17 years ago is suggesting that the risk to subgrade soil acidity is increasing, we're now seeing significant research into that issue and ways in which to try and manage it, which is much more difficult than just surface acidity in topsoils. So it's a major environmental and economic concern. Significant amount of Australian agricultural land has pH values less than optimal for the crops that are being grown. And again, that just referencing that point that I made just a moment ago around subsurface soils and the challenge and expense that might be required to amend those soils for maintaining and increasing crop production. So we touched on in video one the soil pH and the role that it plays in soils. And probably in many Australian soils, it is the master variable. It is that number one issue around production constraint. That and these are a couple of reasons why. It has a significant influence on soil microbe activity. It plays a very large role, as we looked at with the pH chart that you can often find in different forms of nutrient exchange within soils, has a significant role to play there. Therefore, nutrient availability as soils become more acid, as we touched on in aluminium in video 1, nutrient availability of aluminium increases as acidity increases, impacting plant growth, impacts gas exchange, chemical degradation from products that we may be using, and impacts the cation exchange capacity of the soil, which is where much of our nutrient is cation nutrient is held in soils, and also then its availability to plants. Here's a couple of important points around acidity. It is a measure of hydrogen in the soil. So an acidic soil will emit hydrogen ions, holds some on the exchange sites and pushes them into and around plant roots. On a soil that is above pH of 7, so from 7 to 14 on the pH scale that we refer to often, when we measure hydrogen on those soils, above 7 will be zero hydrogen on all measures, and that is because the hydrogen is actually held by the soil and not allowed to come off. pH is also a logarithmic scale. So from looking at that last bullet point there, if our soil pH has 4, then it's 10 times more acidic than a soil with a pH of 5. This is important to understand with the amount of material for amelioration, such as limestone, that we may need to apply to reduce that pH. So it's 4 is 10 times greater than a soil with a pH of 5, and 100 times, because from 6 to 5 is 10, and from 5 to 4 is 10. There's 100 times more acid than a soil at that pH of 6. That's the logarithmic scale. So again, increased expense and increased challenge of incorporation of that ameliorating material that we might be using to help us manage acidity. So important to understand it now and start managing now. As we touched on with the pH scale and why acidity is so important, certainly for the major crops that we grow for food in Australia and worldwide, is in acidic soils, those major plant nutrients become less available. We saw that on that pH chart, and that's why it's important for growers to be familiar with that pH chart that we looked at earlier. Plants can also show deficiency symptoms despite adequate fertilizer application, so that dynamic of the soil will also change, and just applying a nutrient does not necessarily mean it will become available to the plant. So they're important aspects to understand, and getting advice with your soil testing around how those nutrients behave. Just refreshing, that's the chart that we'll refer to as a general guide to nutrient availability. Again, in the middle, roughly there, aluminium behaves very similarly to iron, and that's an important element in Australian soils that we did look at it in video 1. Importantly, for the nitrogen component, which is nitrogen is often the deficient nutrient in Australian farming systems, and the use of legumes in those systems is very important. acidic soils reduce that microbial activity and therefore reduce legume nodulation for rhizobia, which are the nitrogen nodules that collect atmospheric nitrogen and convert that eventually into an organic form and then through to an available form of nitrogen through mineralization, generally during that crop and the next crop there'll be some residual nitrogen. So there's a lot of work in New South Wales researching different strains of rhizobia that will tolerate acid soils, but again that's becoming available presently with trials in paddocks. But that's a very important part of certainly trying to be more efficient and more environmentally friendly, utilizing biology and understanding what that acidity is doing. So limestone application typically is of value there, and putting that limestone on will not only improve nutrient availability in the soil that you're working with, but also some of this microbial activity that we're looking for specifically around rhizobia and many others. This is just one example. Soil acidification is a natural process of that is accelerated by agriculture. Rainfall leaches some basic ions of calcium, magnesium, potassium away. Carbon dioxide from decomposing organic matter and rainwater form organic acids. Again, these are hydrogen ions that are left behind through that decomposition process and natural cycling in the soil that contribute to acidity very slowly, but contribute. And again, the use of nutrients, ammonium and sulfur fertilizers also contribute by leaving hydrogen ions behind in the soil to increase that acidity. There's also the removal of nutrients that will assist in increasing the acidity also. Typically, and most soils, and we do need to be careful when we're making these blanket statements around 2.5 tons on a heavy clay soil up in Stanley, we can probably apply a little bit more. The important thing is there in bullet point 2 is that limestone, if that's being applied, need to get that in contact with the soil, so as much of the soil as possible. So that requires, in most instances, some tillage. There are liquid products becoming more available and relatively efficient in pricing and application that will penetrate the soil a little bit better. But again, that's very important to see that incorporation, whatever rate is being applied, to get as much soil contact with that ameliorant as possible, to be capturing and holding the hydrogen ions that are measured for acidity. But just touching a little bit there on calcium carbonate, which is limestone. The carbonate is what actually captures the hydrogen, so it becomes a different chemical nutrient there, and that's what traps the hydrogen. It doesn't let it go. So that's the bit that we're reducing that hydrogen from the soil, and that's what the limestone does. It's still important to understand that the mineralogy, the clay fractions, organic matter, cultivation are all important in understanding how that limestone will work. So we can measure something quite specifically in the lab, but then there's a whole lot of variability when it gets out into the paddock with types of lime that are available, the soil type more specifically, how you're going to try and incorporate that as a grower. Certainly in tree cropping systems, that's a little bit more of a challenge than even limited till systems like broadacre cropping. I recommend that when you're getting your soil test done, that you do a buffer pH. That's a test where an amount of calcium or amount of an alkaline is added to the material a known amount that can then measure how much impact it has, and then we can calculate more appropriately lime rates based on that buffer pH of how much you might need before you can start to move pH around. So that's just, I'll just touch on that. There's a bit more information there than what's necessary really, but a pH buffer test I would be recommending with your soil testing. When it comes to lime, and lime is probably the most easily accessed material, it will assist in reducing pH. The shot is to get the finest material, typically the finest material that you can, and then look at how you're going to get it incorporated and mixed with the soil. But the finest material, and that will also comes with a budget penalty as well, a cost penalty, where finer materials are often more costly because it's denser to transport, and depends on the amount of effort that's been put in to grind that material down. There's still the old adage of 100 millimeters of rainfall to activate lime, and that's really about the hydrolyzing process of getting the limestone wet so it then can start to break down and get into the soil and become part of that soil solution that we touched on earlier. So that's all I've got there, just touching on acidity and limestone, just very briefly, and we're trying to keep this moving through as just an introduction. We'll work through now into some matters around soil erosion, which is probably a big one, probably more a concern in the hill country of northeast Victoria. So erosion is a process of detachment and transport of soil particles by erosive agents. And what we're referring to there is erosive agents as being water, wind, and tillage. Now these, in an agricultural environment that the northeast is, all of those impacts, all of those managed components and non-managed components provide a big influence on the erosion risk that we have. When we look at on-farm damage due to water erosion, it's the loss of organic matter that is being washed away in the soil surface, and that organic matter holds a lot of nutrient. So it's nutrient that we've got from the cycling of our tree crops, in particular in this instance with chestnut growers, that then further exacerbates degradation, surface compaction, it reduces that water infiltration. So you can go through that list there and see some pretty serious issues in terms of management. From a catchment management authority point of view, there's even greater risk more broadly and off farm, which is what they're looking for growers to take into consideration and to begin improving their management. And that's the water pollution by carrying nitrogen and phosphorus particularly, which are higher use products in our agriculture, getting them into waterways, contributing to fish kill, flooding, carrying lots of material, burial of infrastructure, and damage of infrastructure, and the silting up of rivers and restricting water movement. So there's some off-farm issues that the catchment management is going to be very well aware of, that we do need as growers to ensure that we're managing to assist the environment. This is the most common, just a couple of images now, just the most common erosion risk that we would see is just water carrying sediment. Whether this property has got vehicle traffic and has worn ground cover down and that soil is being moved, or whether it's livestock that is overgrazing property. Just very simple measures that are contributing when rainfall falls and then carries that water filled with soil off the property. More more broadly, we're very familiar with this around the Northeast District, and it is something we contribute to in some ways as growers, and also have a responsibility to improve our management to reduce these risks. And then, of course, moving into larger issues of gully erosion. Not good for any of our productive land. This is a picture from Mildura there in the last couple of years of these dust storms carrying very, very large amounts of soil, and even to the point where that dust was able to be measured as impacting air quality in New Zealand. That's not the thing we want to see that agriculture participating to, and certainly there are ways of us to improve our management to improve that. So what's causing soil erosion? We've probably touched on those adequately, and I won't spend too much time on it. Removing plant cover or losing plant cover either by traffic, livestock overgrazing, under our trees in large chestnut groves, there are very limited light for plants to grow. So there are other ways in which we can lose ground cover. Cultivation practices, and we've touched on all of those, and the rain and water runoff, certainly in high rainfall areas like the Northeast, contribute to that too. In respect of soil texture, this is the physical component that we looked at those earlier slides in video 1. The real issue that we see there is these very, very small particles of silt and clay that the energy that's contained in water flow or rainfall can dislodge and disaggregate these mineral particles, and then they exacerbate erosion and disaggregation on the soil surface when there's water present and flowing. And this is where we see an exacerbation of that erosion risk. So what we looked at of those in video 1 was the organic matter contributing, and glomalin particularly, as a measure of that, as a glue that's holding our aggregates together. Calcium also plays an important role in helping soil aggregate, and they, by measuring the soil, which was really the emphasis that first part of our video 1, measuring our soil, understanding what's happening there, we should be able to begin managing and improving our management much more than what we're probably looking at nowadays. It's just looking at, or commonly looking at a soil test of what nutrients do I need to apply for my crop. We can have a broader discussion around measuring our soil and understanding some broader aspects of what that soil test is also telling us. So I want to just touch on a micro aggregate. We're looking at a large number, and we can see here, we'll just touch on the silt and clay structures where these two little bits on the legend there. So there is a large combination of those mineral aggregates or minerals in that aggregation, and that micro aggregate or macro aggregate in this instance has got a root growing through it, and microorganisms are also in there, and organic matter that's represented there. That's what a micro aggregate is. The better that is aggregated, the better our soil will perform, and the reduced risk of erosion. So I think that most growers will start to see more information become available in respect of aggregation in soils, maintaining that aggregation, because it can be crushed, so the aggregate that's next to it can be crushed with compaction, and there are areas for us to look at, continue to improve our management. So the process of water erosion, just taking those previous couple of slides, raindrops striking bare soil and dislodging particles, that's probably one of our greatest risks in the Northeast with our high rainfall environment. The rain can also seal. We touched on that with compaction and water infiltration earlier. And then rainfall that exceeds the infiltration capacity of the soil then starts to flow across the ground. That is what's carrying moisture off property. Just two other, beginning to wrap up now, two other issues. Salinity is often closely related to soil degradation, as salt inhibits that aggregation. So fortunately, again, as in limestone, gypsum and as a calcium source and a sulfur source can contribute to reducing that salinity in the surface, but that's a bigger issue. But certainly salinity is an issue that can contribute to erosion very readily. And soil compaction, that we've probably spent a fair bit of the discussion today, other than pH, compaction, that next major influence on our soils in respect of erosion risk. Just to wrap up, this is just a very small demonstration that we had at a chestnut grower's property. So a small amount of microlena seed was just thrown on the ground. Here, it was not any particular effort to seed it in, so it was just laid on the ground. There was rainfall and we lost a little bit, but you can see how vigorous that growth is there and how dense it is, even for a grass that's very, very young. And we will be working with this grower to take that microlena through more of the property. And you can see, this is exactly what we've been talking about in both of these videos that we've presented here. The bare soil and very sparse growth that does exist under mature chestnut trees. If we can get a bit more of this in, and this is Microlena stipoides from Native Seeds. I'll give them a plug for their contribution and cooperation in helping us with this demonstration. We'll be taking, and as I said earlier, we'll be taking this grass and planting some more through that chestnut orchard and seeing if we can get some better management of that soil surface and orchard surface. So that's really all I've got. I'd like to thank you for watching. Again, hopefully through 2021, some opportunities will come up to get into a little more detail around management. If they don't, we'll be going back to the video and put some more detailed information up. Keep following along, and we look forward to any questions that you've got. Thanks very much to the Northeast Catchment Management Authority, Chestnuts Australia, Trevor Ranford and Connexus Global for the opportunity to participate in this project. We hope it's been briefly informative, and certainly it is only an introduction to a major topic of soil management and just these two aspects to improve crop production for our nut growers and the northeast of Victoria. Thank you very much.